All right, hello everyone. Thank you for the opportunity to speak. So today I'm going to be describing universal approximation with deep narrow networks. So I'm going to start off by describing the classical universal approximation theorem, and then I'm going to move on to discussing what I mean by, in some sense, a transposed universal approximation. I'm going to introduce some applications and some extensions of our main result, and then this is going to motivate some open questions. So first things first, what is the classical universal approximation theorem and why should you care? So what this says is that given networks of this type, which are wide, shallow, single hidden layer going as wide as we like, with a non-polynomial activation function, that neural networks of this type can approximate any continuous function. So this is one of these absolutely key results. It's one of these fundamental results about answering the question of why do neural networks work? Because it says that it doesn't matter what you're doing, what problem you're considering, what task you're trying to solve. In principle, a neural network can do the job. So formally speaking, the statement of this theorem is that given some continuous function, and then considering the class of neural networks with this as the activation function, with n neurons in the input layer, one neuron in the output layer, and the one hidden layer going arbitrarily wide, then, in fact, these neural networks are dense in the continuous functions if and only if rho is non-polynomial. We get universal approximation with these networks if and only if rho is non-polynomial. Okay, so networks of this type aren't really what we tend to use in practice, right? And if nothing else, we're going to start adding extra hidden layers. Do we still get universal approximation then? And in fact, actually, yes, we do. We can apply the classical theorem here as well. And the way this can be seen is that the first layer, we can apply the theorem to have it approximate whatever function we wanted to approximate, whatever our target function is. And then the second and third and so on layers can all be approximate the identity, which they can do by the theorem. An identity is a function, we can have them approximate. And so collectively, what this then means is that the classical theorem applies to bounded depth arbitrary width networks, which I'll refer to as shallow wide networks. And so this says nothing about the efficiency of going deeper, but it does at least reassure us that we've not lost anything by doing so. Now, given this description, I think there's a natural question which the title of my talk rather gives away. And that question is, what happens if we take all of these hidden neurons, all of these blue dots in the middle, and turn them all around? And so instead of shallow wide, we have deep and narrow. So this is really why I'm describing this as somehow transposed. What happens now? So the first thing we have to be aware of is that we have to explicitly consider multiple output neurons. Because in the shallow and wide case, back here, if we had multiple output neurons, then we could just apply the theorem multiple times, get multiple arbitrarily wide networks, and just put them side by side. And side by side arbitrarily wide networks is itself one arbitrarily wide network. But the same isn't true here, because we're going to try and control our width. We can't just put things side by side. And anyway, do we get universal approximation? And as you probably guessed by the fact that I'm giving this talk, the answer is yes. Yes, we do. But we do have to think also about what kind of result are we expecting to prove here? What kind of questions might we be answering here? Because, for example, what activation functions work? In the classical case, it was both necessary and sufficient that the activation function be non-polynomial. And it's going to turn out that the same isn't true here. It's going to be slightly different. Next, we might ask how narrow the network can be. What's the width? Because if we have n inputs, and then we have a width of only n minus 1, then the first thing we do is a linear map from an n-dimensional space to an n minus 1 dimensional space, from a higher dimensional to a lower dimensional space. And so this linear map must actually have non-trivial kernel. It must have some hyperplane that it doesn't see. So we can see that if we go too narrow, that in fact we must lose universal approximation. There is going to be some critical width. And then we might also ask what density, what kind of topology are we going to be seeking density, universal approximation with respect to? Okay, so there's one definition I'm going to introduce. This is one piece of notation, and I promise you it's the only piece of notation that I'm going to introduce in this talk. And this notation is, if we consider this class of deep, narrow, feed-forward neural networks with n neurons in the input layer, m neurons in the output layer, and k neurons in every hidden layer, and as many of these hidden layers as we like, and activation function rho, then we're able to make the following statement. Given some non-affine continuous function which is continuously differentiable at least one point, non-zero derivative at that point. So this is a technical condition that I'll come back to. Then, in fact, the statement of the theorem is that these deep narrow networks of width n plus m plus 2 are dense in the continuous functions. We get universal approximation in the continuous functions with respect to the uniform norm. So, informally speaking, what this is saying is that deep narrow networks with essentially any activation function can approximate any continuous function. And so I'd invite you to go back to those 3 questions I just posed and see how it answers them. What activation function? So we have this technical condition on the activation function that it should be continuously differentiable at least one point with non-zero derivative at that point. And I'll discuss that more in a moment. But essentially, this is very weak. Any activation function we might imagine using in a computer will satisfy this property. Next up, the width. We explicitly specify that as n plus m plus 2. And then what topology is the uniform topology, which also implies LP topologies as well. And there's one main trick we're going to be using here, and it's based off this technical condition on the activation function. So I'll state that again, continuously differentiable at least one point with non-zero derivative at that point, saying that locally there's some point where we look like a non-zero straight line. And this is then going to allow us a composition of a linear map with the activation function with another linear map to approximate the identity function. And this is possible because we can use our first linear map to zoom in on this little point where we know that we look like a straight line. Then we pass through our activation function, which is locally linear, approximately linear. And then we use our second linear map to zoom back out again. And so overall, it looks like some linear map that we can control. And in particular, we're going to ask that it look like the identity. And at this point, I'm going to be able to use this trick to present a sketch proof. I'm aware, of course, that the point at which a presenter starts talking about their proof in technical detail is the point at which everyone switches off. So in an effort to keep things interesting and sort of visual, I'm going to be using these pictures like this, or proof by dodgy diagram is the way I've heard it put. So we're going to use dots to represent scalar values and arrows between them to represent the action of a linear map composed with the activation function in the way that no doubt you've seen in hundreds of neural network pictures already. So we're going to start off with this trick I've just described with the identity function to copy our inputs into the network. And then we're going to do this between every hidden layer. So approximately up to some approximation of the identity, we're going to have our inputs available at every single hidden layer. As a result, we can then do some small amount of computation based off of those inputs. And then we're going to add them up. And this adding them up is also possible because we have a linear map. Linear maps can add things up. And then we can basically just apply this identity trick again to pretend that our activation function is the identity. And then we're going to repeat. We're going to go up a layer. We're going to do some small amount of computation. We're going to add things up. Go up a layer, small amount of computation, add things up, and so on. And then eventually, when we get to the end, we're just going to map that to our output. So at this point, I think it's this intuition that we're using here, that we can add up lots and lots of little things in order to approximate any function. This is actually the same intuition as applies in the classical version of the theorem. Because in the classical version of the theorem, we had this one hidden layer, and every neuron in the hidden layer did some small amount of computation. Then the output layer added them all up. And it's the same thing here. We do lots and lots of little bits of computation and add them all up. There's another cool comparison to make here, which is to a computer program. And what I mean by this is that certain formal descriptions of a computer program can be written down by considering registers, where you have a straight line going across your page representing some place you can store information, and then lines between them representing operations between registers. And we're doing the same thing here. We've got 2 registers on the left-hand side storing our inputs, and we have 1 register on the right-hand side in which we accumulate our output, and then the computations in between them. This resulting map, this resulting neural network is very sparse. It doesn't have very many connections, and it's also constructive. So in principle, we can find a network doing what we wanted to do. As a remark on the proof, polynomial and non-polynomial activations are actually handled very differently. This intuition I gave earlier, that this is somehow like the classical version of the theorem, actually allows us to prove it in the same way. We can take the classical version of the theorem, and then we can turn it on its side. We can just sort of feed in all of these inputs as we go through layer by layer into one neuron as we go up, and then we just add them all up. But unfortunately, this isn't true for the polynomial case. The classical theorem doesn't apply there, and we need to sort of prove things from scratch. And in this case, there's actually another trick that we end up using, which is that we can approximate the reciprocal in a width-efficient manner. So that's another cool trick, but not one that I'm going to try and describe now. Okay, so to summarize the comparison between shallow and deep, in the shallow case, we had this arbitrary width, bounded depth, and non-polynomial activation. But in the deep case, we had bounded width and arbitrary depth, and we now allow almost any activation. So in particular, we see there's this qualitative difference between shallow and deep with respect to the choice of activation function. So what are some applications of this? If one is proposing a new model, then it's often desirable to demonstrate that this new model exhibits universal approximation. And this gives a new way to do that. And so I've actually already seen a few papers doing exactly that, which is quite cool. And it also gives us an understanding of bottlenecks. In the statement of the theorem, we had this width of n plus m plus 2. And so if our proposed bottleneck is wider than that, then in fact it's not a bottleneck. On the more theoretical side, this statement of the theorem also allows us to handle classes of neural networks which increase in width and depth simultaneously, because we can just ignore the extra width. But the classical theorem doesn't apply here. The extra depth can sort of end up messing with the width in undesirable ways. And then, as I've already said, there's this qualitative difference between shallow and deep. So what are some extensions of this result? So first of all, it's possible to show that most activations can be made, the network can be made slightly narrower. So here we have width n plus m plus 1, contrast the n plus m plus 2 in the main statement of the theorem. It's possible to show that certain non-differentiable activation functions can also exhibit universal approximation, contrast this technical condition on the derivative that we assumed in the main version of the theorem. And we can also show that ReLU activations exhibit universal approximation in a non-compact domain over all of Rn now. Contrast this compact K that was used in the main version of the theorem. So what all of these are showing is that our theorem is giving sufficient but not necessary conditions for universal approximation, and there's still a little bit of wiggle room. And as a result, this really motivates some open questions. And that's things like, can the width be reduced further? So we stated n plus m plus 2, but for example, it's actually known that for the ReLU, it can be reduced to just n plus m. What actually is the precise minimum width? And what I really mean by this are what are lower bounds? Because I outlined earlier how if you have n inputs and then a width of only n minus 1, then you must have some non-trivial kernel. But in fact, it's also known that width of n is also too small via a certain topological argument. And for general non-differentiable activation functions, can we get universal approximation? And can non-ReLU activations also give us density in non-compact domains? And can we get universal approximation with respect to other topologies, in particular, for example, Sobolev topologies? And these are all open questions. So with that, here are some references. So this is this paper I've been describing here. And then this is some previous work on the deep and narrow case. Most of this is specific to the ReLU, and this is really what what our innovation is that we're able to present these results without relying on the friendly algebraic properties and explicit description of the ReLU. And then finally, this is the classical version of the universal approximation theorem for the shallow and wide case. So with that, I'm out of time and out of slides. So thank you very much for your attention. Thank you very much.